I know we only have an hour and a half, and I've got a few things set up over here. And as far as our trainer, I've got a different trainer. So what Judith just said about things being rewired and changed up, that that happens. But the content usually is about the same when we go over, regardless. And with that said, I'm gonna just share a screen here real quick. One of the things that we talked about, I'm gonna stick with these bullets. And the first one is review the trainer configuration, common lines, the switches, the different methods that were completed at the workshop. I didn't want people to be confused with that after we had left, because we pretty much abruptly kind of got out of there that day because we had such a full day. But I want to just kind of share with you a little screen that I put together here. Let me just see if I can find it. I have only 2 screens here. I need about 4. Let me just get. Yeah, so I'm going to share this screen. Tell me if you see it here in a moment. Disappeared on me. Do you see that screen?
Yes.
Okay. So there were a couple ways that and I'm not gonna spend a lot of time on this, but there was a couple ways that were people wired up their machines. And one method that was kind of unique to our workshop, and we did this primarily to save on some of these shorting blocks and to save on some terminal blocks. So what a couple people did is they made their own little shorting blocks here, and you can see this. And if I scroll down here, you can see the wires that are coming in from the load, which is the light, over and into what is going to the common back to the negative side of the power supply. And then, excuse me, the push button switches come into the orange, which again come back and return to the power supply. Then the inputs are coming back around in these white wires where different things are hooked up, whether it be a light to turn on or whether it would be the relay to turn on. An alternative to that is right here, where every input and output are isolated. And you can see that right here. And this particular person used white for the inputs and whites for the outputs. And then when they were going to hook something up, and then here's the bus for plus 24, and here's the common side of the bus for the 24-volt power supply. So if this person were to hook something up, I'm just going to, oops, I'm going to blow this up a little bit. If they were to hook something up, they would tie maybe an input switch here, right? And then they would tie the load back to here and go back to their load. And so they would individually turn things on, where this person has everything kind of tied together. There can be some limitations to that. For instance, if you wanted to have everything current syncing, it's a term we use, or everything current sourcing. And it all depends on how you tie things up to the power supply. And in this case, everything here is being tied back to the common side of the power supply. So each of the loads are going to be sourcing the power. So that means you have to tie the loads up to plus 24 volts, and then this completes the path. So the trainer that I'm going to be using, it's a little messy, is this one here. So this one, you can kind of see, I'm going to make you dizzy here, looks a lot like, excuse me, this one here. Everything is isolated, very clean. And so when I come back down the mine, everything here is isolated. I'm just happening to use triple tiered terminal blocks, and it saves on a lot of real estate. So take a look at that. I'm going to scroll back up, and you can see where everything is spread out here. I can do the same thing in half the space, but remember, I've got double input switches here, normally closed, normally open for each one of these. And remember, red was normally closed, and green was normally open. So every time I push the green switch, I'm either opening the red contacts and at the same time closing the green contacts because they're mechanically tied together. So literally I could cut this in half and get by with just this because I'm doing triple high terminal blocks. Does that make sense? And sometimes
Yes.
we do that when we need real estate space on a board.
Mhm.
Okay. So two different methods. They're both okay. So when people left that workshop, I didn't want them to think, well, why did this gentleman do his like this and I did mine like this? This way is a little bit maybe more preferred because it's a little more clean because everything is isolated. Okay. Any questions on that?
No, makes sense. Thank you.
Okay. I'm gonna stop sharing my screen here. As soon as I find the Zoom. Well, this is interesting. I see everybody, I just can't. Oh, there it is. Gosh, it's hiding over here. Sorry about that.
Okay.
It was on my other screen, way over there. Okay, so the next thing we said we were going to talk about is we were going to talk a little bit about force sensors, read switches, and light detecting resistors and their physical makeups. We pretty much spent our time wiring the trainer. We didn't have a whole lot of time to get into, these other little pieces of circuitry that are more fun than anything. And they all serve a purpose, obviously, these little sensors that I picked. So when we talk about like the breadboard, there's some industry people who would say, you don't need a breadboard on our trainer because they don't use breadboards in industry. But if you're going to be teaching, and Andreas, you probably, and maybe even um, Ernie, and I mean, you probably teach them this because you're doing things with your little controller. So you have to be able to bring wires in and so forth. So I like it as an interface. And the way I teach my classes is we use it temporarily to do certain things like what I'm going to show you right now. And then after that, it kind of just goes away. So I'm going to change my camera view. I'm going to turn this camera off. Okay, so can you hear me over here? You can hear me? I've got a second microphone here.
Yes, we can hear you.
Yes.
Okay.
Perfect.
I'm going to cover this up because I was noticing that I was getting some bouncing with the light reflecting off of these silver terminals here. So
I mean, it look okay to me, even without you covering it.
yeah,
Mhm.
we'll try it like that. It doesn't appear to be bouncing right now, so I'm just going to hook something up here. Okay, so I've got a board here that I'm gonna play with. And so first thing we're gonna talk about is the force sensor. And the force sensor, as I apply force, obviously it changes the resistance. And what I've got built up here is that little LED light that you guys also have in your kit. And the interesting thing about a force sensor is
Oop, can't hear you.
the interesting thing about that force sensor is its properties, and I'm going to pull up a data sheet here and show you kind of why it's important to have data sheets. And when I'm doing my training and introducing kids to different components, I make sure that they understand data sheets. So one of the things that I want to show you here is just this one really quick. And I'm going to share my screen again. So I'm going to be jumping back and forth here. So I kind of apologize for that. And you can probably see that now. So where I want to take you is just kind of the physical makeup of this device. So basically it's a variable resistor. That's it. And some things are sensitive to light, some things are sensitive to pressure, some things, are sensitive to other things. This is heat. This one is sensitive to pressure. So what happens is this integrated circuit that's printed on here changes with a force. In industry, we use things like strain gauges and those kinds of things. They put them under bridges, they put them in skyscrapers, and as that strain and stresses, we can get a different resistance, and a very sophisticated bridge circuit can denote any change in that current that's flowing through the circuit, and it's an imbalance, and then we know there's something happening. Same thing here. The nice application about this one is you can make a voltage divider. So in my case over here, all I'm doing is I'm just changing the resistance of the circuit. And I'm going to go down here to page 15. If you don't have this, I'll include it. I'll send it to Marilyn. But on page 15 is where kind of the important stuff is. And it's telling us that the standoff resistance is greater than 10 meg. And I will tell you that last night at a very late time, I was trying to get both of my Fluke and my Klein, which are very top-notch meters, to read this sensor. And when they say it's greater than 10 meg, I think it's greater than about 30 meg. So basically, it's infinite. It's just like an air gap. So, but when I start to touch it, when I start to squeeze it, that resistance drops immensely, very quickly. So the way I use these with my students is I give them a chart and I say, okay, this thing is just infinity. It's not even in the circuit. It's so great, the resistance. I want you to build a voltage divider. And Andreas, you'd appreciate this. So I have them build a homemade 0 to 10 volt analog input to a PLC, or in your case, to a little microcontroller. You got to be very careful with that, because if you exceed the voltage, right, if it's a 0 to 10, you can burn out an input. So they're very careful about calculating that voltage divider. So if you don't know what a voltage divider is, if I have 24 volts and I have a 1K resistor and a second 1K resistor, and I tap right in the middle and tie my positive to the top and my negative to the bottom, essentially in the middle, I will get 12 volts. I'll drop 12 volts across one resistor and 12 across the other, and I'll get 12 in the output. If I replace one of those resistors with my force sensor, I can squeeze and I can watch that voltage climb, because the resistance is dropping. And depending if it's the first resistor or the second one, I can show that either climbing or dropping. So when you have your trainer and you're playing around with it, set it up as a voltage divider. And I've got labs that I think I sent home with you. If not, I'll give them to Marilyn, that shows you exactly how to do that. And I even tell you to find that optimum resistor at 24 volts of how to get that 0 to 10 swing. Okay. So I think yeah, I'm going to stop sharing this because I think that's enough of that. And I'm going to go back over to my trainer, I think. Matter of fact, I think I'll just do it right here. I'll save us a little time from jumping back and forth. Okay, so here's basically another one of those circuits, right? And I'm gonna set my meter to ohms, and it's in overload right now because it's trying to read like 6 meg. And so I'm gonna connect my meter up to this, and I have it on my breadboard over here a little bit better with little terminal blocks. But what you see here is overload. In other words, it's an open. It's like it's like the leads aren't even connected to anything. And as I squeeze this, I'm just going to hold this up. Like I said, I got it set up better on the other side. You can see it changes into k ohms or kilo ohms to the point where I can squeeze it so far down, it almost zeroes out. And I'm doing it kind of hard here, but that's like 216 ohms. But if I let off just a little bit, I can get that where I can get a swing of however I want. So imagine this on a bridge embankment somewhere where the pressure is being pushed down. And if it exceeds a certain amount or doesn't exceed a certain amount in traffic time, they know there's something going on with that bridge, or even they can monitor sway of a high-rise building with a strain gauge. Some of these are built where if I tweak it and twist it this way, it puts a strain on it, changes the resistance. And those of you who have played with microcontrollers or PLCs, like what's up there blinking behind me, you can do some pretty amazing things with a very inexpensive $15 sensor like this, as opposed to a $400, $500 strain gauge. Okay. Okay, so at rest, doing nothing, probably 30 meg, infinite. When I apply pressure to it, it starts to drop very quickly in ohms in the K ohm region, which then is something we can use, right? And I can get it to the point where I can squeeze it so far down, I can make a light get brighter and brighter and brighter, like you saw over here. And that's kind of my lab. And that's the lab that I have right now. It's infinite resistance. But when I start to touch it, you can see the light get brighter and brighter if I squeeze it. And that's because I'm changing that resistance of that circuit. Okay.
I think you're muted.
We can hear you.
You just left us, yeah.
We still can hear you.
Now you can.
Yes, yes.
I have
Yeah.
a two-stage muting process here. My Yeti mic, when I change back and forth, it shuts itself off. I guess it's a safety, but
I have
so
a
the other,
question.
what's that?
A question.
Yep.
I had a quick question about your sensor that you were pressing upon. Is there any input from your biochemistry in that particular
No,
press? Okay.
no, it's not heat. It's not moisture. It's just pressure. And you can do that. Matter of fact, remember our calibration tool? And this is how you would, because people would say, well, you know, you squeeze harder than me, so how do I set this thing up for that 0 to 10? So here's the way to do it. Just take your clothespin and put it on there. And now it's set to a specific, and I'm not going to say that's repeatable, but it is repeatable. I mean, it's a spring, but it's a very low cost calibration tool. And I never even thought about using it in class until I came down to Florida, and I thought, oh my God, a clothespin, that's brilliant. I'll do that because, you know, you got me that maybe can squeeze things, you know, like somebody that can take a lid off a ketchup bottle and somebody can't. Well, how do you do that? Well, you use a clothespin. So you guys all got a clothespin in your little bag that we left behind. So that gives you a very calibrated method to just turn the light on. If you want to say, okay, with a voltage divider with a 1K resistor in series with my force sensor, as long as the clothespin is on, this is the resistance I get. So from there, you can call that your standard, and from there you can build your chart of different pressures and such like that. So does that help, Judith?
Yes, that's perfect. Thank
Okay.
you.
So while I'm over here, I'm going to connect up to our light emitting sensor. And I've got some really nice leads here that I can tie to. And with these, I'm going to put I think you can see that. As I cover this, you can see that the resistance once again changes. So this is a whole different technology. This is light. And I've just got ambient light coming in. So when you're testing these, you can do 3 tests. One would be maybe direct light, ambient light, and dark. And if I just put my hand over the top of it, it goes to about 30 kiloohms. When I just do ambient light, it goes to about 33. It's jumping back and forth. Let me just see here. I'm sorry. It's 2 meg at this point, and at this point it's 34 kiloohms. And now if I shine a light on it, because you have a flashlight too, it drops down to 700 ohms. So you're going from almost 3 meg down to 200K, down to hundreds of ohms just by whatever's happening with ambient light. And it's very sensitive to that. These devices are pennies. You can get them for a few bucks. And when you think about the traffic light, or excuse me, not the traffic lights, but the street lights that are outside with that little dome on top, there's nothing more than that little sensor in there, or those little lights you plant in your garden. They have a circuit with a transistor that says, when this goes dark, turn the transistor on and make the light come on, right? That's exactly how they work. And if you go home and look at those ones that are along your pathway, you'll see a little circuit like this that's exposed to the sun. And that's what's causing that to happen. So in the dark, I've got 2 about 3 meg. In ambient light, I've got 23K. And in bright light, I have 700 ohms. The last one I want to talk about, and then I'm going to come back to this this light one and how you would use it in a circuit. I'm going to connect up to the reed switch, and I'm going to go to continuity. So I'm just going to have this connected up. I'm going to take that little magnet that we gave you, and I'm going to go across the reed switch, I think. Yep. And you can hear continuity just by me bringing this magnet in close proximity. There are much more expensive, and like this sensor here is one that's like it. It's back here, it's a Prox sensor, Allen Bradley, and you can either spend a few pennies for this one back here, or you can spend a couple $100 for the one that's in a better package, but it works the same way. You put it in, you've seen them for door alarms, where you have the magnet on the window, and then tied into the sill or into the frame of the door, you have the circuit such as this. Laptop computers were the same way back in the old days. They had a magnet in the lid, and then down by the keypad where the mouse was, they had a circuit, and when you closed it, that magnet made the re-switch, put the computer to sleep. It was a very simple little circuit.
So when I had windows put in, we have a ton of those. I could repurpose to do something in class with this using the sensor that's in there.
Yeah. Yeah,
Good.
yeah, you could. You could, yeah, repurpose them and do all kinds of, I mean, now I think they got away from the magnet. I think they might use, a different proximity sensor, a Hall effect sensor, which is kind of a takeaway from the reed switch. The reed switch is just discrete on or off. There's no in between. I mean, magnet strength has nothing to do with it. The magnet's there, it closes. The magnet's away from it, it opens. With a Hall effect sensor, it depends on how large that field is, eddy currents and those kinds of things. So I can make it kind of turn on, think of it like a hose. I can squeeze the hose and make so much current come through, so much amperage, sorry. And I can let off and I can have it flow even more. So I think they got away from, just because, you know, kids probably were figuring out they could take a magnet and turn the computer
Yeah.
off and on and
No,
mess.
these are definite magnets. Yeah. So
Yeah.
good. That's
Yeah.
good to know.
I want to just look at our little punch list here. The main thing we were going to talk about today was relays and that circuit that we never got to play with. And I know I'm talking to some people who are probably very familiar with the technology that I'm going to get into with this relay, but we all went away with a relay, and after the 3 labs, the result was going to be we were going to achieve a latch or a memory, depending on what school you went to. Some people call them memory circuits, some people call them latch circuits. So that circuit, I'm going to share my screen again. I'm going to call up the first lab. Let me,
Are those 3 labs that you sent us that we
yes.
were, okay, got it.
Yep. And the first one, it's part 1, and it's just a PDF. I'm just going to open it up, and it's kind of the anatomy of sorry, I really do need 4 screens. Okay, so you can see the screen now. So basically, I just kind of want to talk about really the 3 parts of the relay. And I think, can you see that on my screen?
Yes.
So I think you have this, but there's a coil, and the coil obviously can either be AC or DC. The ones we're using are 24 volts DC. And a lot of times, you know, depending on what kind of relay, you know, you have this one too. What kind of relay you're using, the documentation, if you don't have it, it's very poor. It's just like people that go out and they troubleshoot motors and transformers. If you don't have a pinout or a legend, you don't know what's what. The only way to figure it out is with our handy little multimeter. So can anybody tell me, regarding a relay, if there are 1, 2, 3, 4, 5, 6, well, 1, 2, 3, 4, 5, 6, 7, 8 terminal blocks on here, what I would expect to see for the coil if I hooked the meter up to it? If I were hunting around to try to find the coil. I'm probably not asking it very good, but you'd expect
I wouldn't be able to, no.
you'd expect to see a resistance, because if I'm checking contacts, right, it's either going to be open or it's going to be shorted. So I have the anatomy of this is I have a coil which has a resistance built into it because it's inductive.
Yeah.
I also have a common contact that is tied to an armature that swings back and forth like on a hinge. And in one state, and I call it at rest. When it's at rest, just sitting like this contact right here is normally closed. This one, there's an air gap there, it's normally open. But when I energize the coil, this swings over magnetically, and now the normally closed contacts are now open, and the normally open contacts are closed. Excuse me. So, and we can get very elaborate the relay that you have on your board back here has two sets of contacts, two normally open and two normally closed, which allows us to do the lab that we need to do that for the latching circuit. So if I come down here, here's our schematic, if you will, of our relay. We have a A1 plus and an A2. That just happens to be the coil. This manufacturer has done a very good job to help us really easily. The terminal block, or excuse me, the socket where the relay plugs into. See if I can open this one up. Here's the relay. Here's the socket. Sometimes they don't number them very, very well. This particular company, the one that you have on your board, they've done a very good job, and there should be no secret about it. I mean, if it helps you troubleshoot in the field, why not make it very easy? They have marked right on their socket these numbers, which you can read very, very well. So you just need this legend right here to tell you that the coil is A1 plus and A2. And why is it A1 plus? If you're saying, well, geez, Doug, it's an inductor, can I just switch the plus and the minus back and forth? Some you can. This one you cannot. And this one you cannot. They have an LED in there that tells you that it's on. They also have a little feedback with a diode that if inrush current or amperage comes back, it protects the circuit so we don't get this negative regenerative force. So if you know what happens with a capacitor when you charge it up, it holds a charge. When you release the power supply, it holds the charge. With an inductor, when you release the power supply, it goes in the reverse EMF, reverse force. So you could have damaging current flowing through the circuit or damaging amperage coming the wrong direction and take out some sensitive device. So they put some protection in there called a diode or an LED.
Doug,
Yep.
I'm so sorry for interrupting. I need to have a restroom break. Would you give us like 2 minutes?
Sure.
Thank you. Or you can continue and I'll just catch up. Sorry.
Okay. Yeah, you'll catch up.
Or can I ask a question real quick?
Yeah.
When I'm looking at your labs that you gave us before, and for instance, this one, where in the beginning it says to watch different videos. Are those videos included in that folder? I see videos, but I wasn't sure because some of them are named a different.
Yeah, and I deleted them from I redid these this morning with your new relay that you have.
Oh,
I
okay.
have no problem supplying those videos to you. I
Okay.
thought I sent a number of them to Marilyn on a shared drive or something.
You did share those. You shared videos in the labs. I guess my question was just with the labs, the PDFs and the videos that are mentioned up front. I just wanted to make sure that those videos are in that same folder.
And
but
if
they
they're
might be
not,
named-
I'll send them because like the lingo one, but I have a relay one that what I'm doing right now, it goes through systematically and talks about exactly what's happening in the circuit.
Oh, okay.
So it's a nice little video to watch.
Okay.
Because it talks about all these elements.
Excellent.
And whether or not it's a motor starter contactor, you know, that runs an air conditioner outside, or a very small little reed switch like you have here, relay, or what they call an ice cube relay, the technology is all the same. Once you learn one, you've learned them all.
Okay, great.
So here is our
Doug,
got this
Doug, so
that
Doug,
number?
how about, sorry for interrupting it also, but maybe at sometime at the end or towards the end, we should stop and go to that folder and just see what's in there, because you did share a link with where there's
Yeah, I'll
all
try
those
to,
things were, maybe we
yeah,
can
after
just
we're,
see.
oh, you found it?
Or
After we're
afterwards,
done
fine.
recording, I'll because I
Okay.
think it,
Okay.
it might be painful for me to try to find that, but if
Oh.
Judith has it, if
Got
Judith
it.
has it,
Okay.
Yeah, I do have it. Thank
Yeah.
you.
So in this beginning lab, it's just in lab number 1, it's just asking you to identify, where these pins are at. But basically, this A1 is saying it's the positive side of the coil. A2 is the common side of the coil. 13, you could call that, the common of the normally open, and 14 would be the other side of the normally open. But it's pretty much explained right here. The reason I have this table in here is because when I was using this ice cube relay, and this is one I thought we were going to be using, but this is discontinued. They don't give you the information. So the lab that you see, all those numbers are kind of missing. So you have to ohm it out. And the only way you could do this that might make it more interesting for your students is you could block out these numbers here and say, okay, you go find them with a meter. Maybe they got rubbed off, or maybe it got so dusty you can't see it. But or maybe there's a third-party manufacturer who made this relay socket and they didn't put the numbers on it. That's very rare, but it can happen. So that's why this exercise is in here. Okay, and then the more important thing that I'm going to jump back to here in a moment is what is the resistance of that coil. That's the important part. Now I'm going to kind of talk to Andreas here because this is more in his area. So I'm going to stop sharing this screen and I'm going to go get the data sheet for this relay. And I think I have it stored here somewhere so I can find it I hope I can find it easily. So the specifications on this, and I'm going to just share my screen again. Okay, so share. So the most important part to me of a relay, because I've seen this happen so many times in class. Imagine a big, I don't have it. Oh, yes, I do. Okay, here's a bigger relay, right? I can tell you, because the work this thing is going to do, it has a higher or has a different resistance than obviously this little thing here, right? The physically size is it's just a lot different. So when we look at the data sheets, one of the things that's the most important, and can you see that data sheet okay? Is we find our relay, and I will tell you right now, it's right here. And if you look at the top of the relay that you have on your board, it's marked right on top. You can't miss it. So it's this number right here. And if you look at this data sheet here, you can see that there's a number of things that you can gather from this. And some of it doesn't really matter, but the one that does is sitting right in here. This is crucial. So we know that the input voltage for the coil is 24 volts. We also know, because they tell us, that the resistance of the coil is 820 ohms. You would never, ever, ever, ever hook one of these up to an output device from a controller PLC without knowing this information first. Because what can we derive with these two numbers, just knowing Ohm's law?
The amps.
That's right, exactly. So now let's just say I get my little calculator out here and I go 24 divided by 820 equals 30 milliamps. So now, Andreas, you have your microcontroller and let's just say the output can deliver 3 milliamps.
Mm-hmm.
What would happen if you hook this relay directly up to it?
You're gonna burn it, right?
You're gonna, yeah, I mean, the term is fry. You're gonna,
Yeah, right. Yeah.
you're gonna lose that output.
Yeah.
And I cannot tell you how many times I've had students tie a motor, a contactor that is a very aggressive,
Mm-hmm.
and they fry the output. And it's like, well, did you not? So how do you get around that? You either
Resistor.
broker that with a smaller relay, right? And have it talk to the other relay. And that's not uncommon. It's not uncommon at all to have something like this sitting right next to something like this that tells this what to do.
Mm,
This is going right to the output card, and this is now an interface to tell this larger load to turn on. Okay.
Okay.
Yeah, so I drill my students on this. Pull the data sheet up. Look at this. I mean, there's other things in here that may or may not be that important, but we really need to know what that coil is asking for. What is the demand of amperage that that thing's going to ask for?
mm,
Okay.
cool.
So now, since we know that, we said we were going to build a circuit. And that circuit was going to turn on some lights. And you can see back behind me, I got a red light on back there. And oh, and by the way, I will send you these data sheets. I've got the pinout data sheet, and I have the specs that I just showed you. So again, with that and your trainer, you can hook anything up to it. So the second lab that we had was to identify, once again, the pins, but more importantly was to hook up the relay. Now, these numbers on here go with the ice cube relay. I'm sorry, but I can redo all these since we have a better relay now, because again, these are discontinued. I love these. I don't know why they did it, but they're gone. But the one we have, I'm getting used to it because I like the nomenclature on it. I like the legend. I like the way they call everything out. It makes it very easy. So this one, we were going to build up like this. So I've got this circuit built behind me. Okay, so I'm just going to turn the other camera on real quick. I'm going to stop sharing. Oh, let me just share again. So you see something here that's kind of familiar, right? That we just had with the other lab one. You see a normally closed contact, and then over here you see a normally open contact. And you see what we call the common, or the armature, that swings back and forth. That's on a spring. So the spring is holding it in position right here, but the coil has enough energy to overcome that spring to pull that back and to open those contacts and close these contacts. So right now, the red light is on. In the resting state, the coil's not energized. And when I push this button, it energizes the coil, and the armature swings over and turns on the green light. So I'm going to stop sharing. Well, you see my red light on, right?
Yeah.
So when I push the green button, and you see the indicator light over here on my relay, that's telling me it's energized.
Mm,
If I had those reversed, A1 plus and A2, it wouldn't work. So normally closed contacts, normally open contacts. Okay. And when I release, it goes back to its default or at rest. This is on and this is off. So now the question is how do we make this stay on when I momentarily push that button? So did I send you that lab? Did you guys get that lab, or was I kind of teasing you with that one?
I was looking through the labs you sent, and I don't know if you've taken some things down from the shared drive, but when I click on a couple of them, they just kind of spin. So I don't know if they're still there or not. So I'm going
Okay.
to check one other place.
Okay. Well, one of the labs that I sent you, and I'm going to share my screen again because this was it. This is what you would share with your students, because this is a brain teaser. Now, some kids might get it right away, but I can tell you it takes a while for some kids to make sense of this. So what you want to do is you want to build what's called a memory switch or a latch. And you want to do this by hooking everything up. And And if you tell your kids this, or your students, if you think about it from just a logical standpoint, it kind of makes sense. It's like when you tell a student to hook up a three-way switch, right, in a house. Some kids can get it like that, and some have to draw it out, and it takes, and they'll never get it. And that's understandable. I mean, the travelers and the neutral and all that. I get it. But this one is so simple when you think about it. But yet it can be so complicated. So I think I specifically maybe didn't send it to you because I knew we were gonna have this virtual meeting, and I wanted you to think about it first and figure out, well, what would make this happen? How can I make this happen? So it's all spelled out right here. Now I'm going to change these pins for you guys so it makes sense to your relay. So when you get this, again, it'll make more sense to the students you share this with, or Judith, your kids, or whatever you want to do, because this will be a fun one for them.
Okay.
So I'm going to go back to my machine over here. I'm going to connect up one wire, just one wire that I disconnected to make it do this. Just toggle back and forth. Back up one wire here real quick. I'm going to turn the power off. Okay, so I got the power back on. Nothing's changed. But now I have it where I'm going to flip my screen over. So now the relay's at rest. The little LED is not on. But now when I momentarily push this, it latches. And when I hit the stop button, it unlatches. So how did that happen? It's one little itty bitty thing. And I said I hooked up one wire. That's basically it.
Yeah, I feel like when you explain this to the kids, using logic, PLC, diagrams, it comes easy to them, when you connect it in
Yeah.
parallel with a push button, yeah. Then they're like, oh yeah, to me it's better to explain it that way. We can hear you. We can hear you.
Sorry, this microphone again. I hate to say it, Marilyn, but I set this up like at 1 a.m. last night. Because I thought, well, I don't need a visual aid. I can just show them a schematic. And I thought, and Andreas is correct. It's like, when you see it and you hear the click and you see things happening, and it's kind of cool. So what is that circuit? So let's just take a look at it. So I don't know that I gave you this circuit. And I was kind of doing this. If I didn't give it to you, it was because I was being mean, and I was just trying to see if you would figure it out. But this is it. And it talks about going through and making this all happen again. And here's the circuit right here. Now these lights have to be inputted into here. But this is it. This is the key right here. So without that piece, those two bold blue lines, everything else was the same before. When I just hit the button and it turned on, then I released the button, it turned off. Judith, you have a question?
No question. I'm just watching.
Okay, so look at what's going on here. When I push the start button, forget these two blue lines. When I push the start button, what happens? Now, this dashed line here, that just denotes that these two relays here, or these two sets of contacts are mechanically tied together. They're not electrically tied together, they're mechanically tied together. So when I push this button and I energize this coil, this armature swings over and this armature swings over, okay? So I'm using obviously this one for the work, for the load, the two lights. And a relay is a wonderful isolation tool. I have a control set of contacts here and a working set of contacts here. I could substitute these little lights for a motor or a 120 volt system, right? I could do anything I wanted on this. If I split this right down the middle, this over here is independent of what's going on here. So I can control this with Andreas's little microcontroller, and I can turn on a 240 volt light over on this side. And I would just do it by taking this red line out, and I would tie this up to 240 volts. So I have a control side and I have a working side. And that's what makes relays so wonderfully unique. And that's why they'll never, ever, ever, ever go away. They may not be mechanical anymore, a lot of them. They may be more solid state. And I have a number of those behind me, but I'm not going to go because they look the same. But there's no moving parts. There's SCRs and triacs and those things built into them. So they can last a lot longer because, as most of you know, what happens when a contact closes under load? It can arc and spark. So the life of these relays can be cut short. I'll tell you, I probably shouldn't tell you this, but I have an apartment, a duplex up in Minnesota, and the renter downstairs, there's 2 meters. There's 2 meters, so it's all legal. But when we put the HVAC system in, the downstairs apartment pays for the air conditioning. So with my mechatronics skills, I built a panel. I put in a big 80 amp relay, and I have a PLC inside this, and I brought both panels in. So I have two 30 amp breakers going to the normally closed side of one side of the relay, and the normally open side, I have the downstairs. Okay, so you follow me? So I've got one power supply here, which is the upstairs panel, and a downstairs panel, and they both have a 30 amp breaker. So I tie one of them into the normally closed side of the relay, just like you're seeing over here. So the upstairs is here, the downstairs is here. And on my PLC, because I don't want this switching over when the air conditioner is on, because that's a lot of current. And as it starts to close, it'll arc, and over time it will degenerate, and I'll have to go replace it. So what I do is I switch it over at midnight. So every other day, upstairs pays like on odd days, and downstairs pays on even days. So at midnight, I have it switch. And yeah, you're saying, but well, Doug, what if at midnight the air conditioner is running? I also have a current sensing sensor on the blower. Okay, Andreas, on the blower. So when if there's a current reading, I'm monitoring if the blower's on. So if it's after midnight and the blower is turned off, it clicks over, and it's called dry circuit. And that relay should last until the end of time, because I'm never switching it. I'm never switching it under load.
That's very cool, Doc. Very cool.
It's probably not legal, but it is very cool. It's a very cool thing. Yeah. So
We'll
now,
never tell.
now the people in the apartment, they pay every other day. So they only pay 15 days out of the month for air conditioning or whatever. And if somebody doesn't run it on a certain day, on an odd day.
Yeah.
But yeah, so it switches back and forth. So that's how relays are used. But I could not. So on one side of the relay, I'm tied to the PLC. This side is tied to two 30 amp breakers, 240 volts. But this line here doesn't go back to my low voltage power supply. It ties right up to the 30 amp. Okay. So what do you see here now that makes this latch? What's unique about this is the green push button switch. And all I've done is I've taken that set of control contacts and I put them in nothing more than parallel. So think about it. Right now, it's normally open, right? And I have this side tied to here, and I have this side going nowhere. But when I push the button down, this swings over, and now I have current going this way, or I have amperage going this way, and I have amperage going through here and through here, which energizes this coil. But the interesting thing is, I'm holding this button down. This has swung over, but when I release this, guess what? Power is now coming from the power supply through here, around the switch, and it keeps the coil latched up or energized, and that's what latches it up. So you're basically putting a normally open set of contacts in parallel with your normally open push button switch. And that's it. That's the magic. That's a motor starter. That's a latching circuit. That's it's as simple as that. And you'll have kids pounding their heads trying to figure out. People in industry will pound their heads. They'll say, "Well, I don't do that. I just buy one." They make them.
Yeah.
Well, yeah,
Yeah.
they make them. They make them. But this is a great one for your kids. And if you give them those labs the way I laid them out, I mean, I painstakingly laid them out with lab 1, learn about the relay. Lab 2, just wire it up where I push the button and release it, it turns off and on, and now make it latch. And if they have 2 sets of contacts, which you do, you have one set here. I think this is pin 13 and pin 14. And the other one, I guess I don't have it here. I think it's pin 32 and 34. But, and again, it doesn't, you can interchange those. It doesn't matter which one you tie to, but it's just putting the input switch that's normally open in parallel with the normally open contacts. And the stop switch is crucial before. And that's the only way you can do it is when I push this and open this up, power is removed from here, which makes this swing back. And now when I release it, there's no more power getting to the coil. It's a brilliant, lovely, interesting circuit. And now we have PLCs and microcontrollers, Raspberry Pis, and the cool controller that Andreas is using. So we don't need that. We can just use, memory latches in our controllers, but in the real world hardware side of things, if you don't have that luxury, you do it with relay logic, and that's what we're doing here.
Can I make a quick comment?
Yeah.
Again, thank you again for this. Sometimes, I mean, we suffer from low number of students, and sometimes some students want to take motors and control without the prerequisite is intro to electronics, right? When we cover the relays, But with these 3 labs, actually, I think I can tell the students you don't have to take it as long as you do these 3 labs in your panel, If they do that, then they're ready for motors and control, because they understand the basics of. Yeah, that's great, Doug. Thank you.
Yeah. And I've cleaned these up, but what I'll do is I'll go back into my drawings and I'll put in here I'll put in the correct screw, and I'll make 2 sets. I'll make one set without, and I'll make a key for you guys with. So then they have to fill in which one that is. Like in this case, this would be up here. This would be over here. This would be A1 plus, and this would be A2, right? Over here, this would be probably 13. This would be 14. This would be 31 and 32 or whatever it was. I can't remember.
Yeah.
But yeah.
Cool. Thank you so much.
Yeah, but it cycles them through where they first learn, oh, okay, the anatomy of a relay, I get it. It's there's this armature that swings back and forth, and you can even look inside of them. You can look inside of them. You can see the spring pulling that contact over. And then you can say that coil has to have enough resistance to have enough amperage to overcome that spring and hold it in place. And then you got to also remember, do I always want to have a relay on, energized? Because that is consuming energy, making heat. So that's why I've really kind of gone away from using a lot of these over to using solid state. No moving parts, and they draw less current and amperage. And I got Richard's got me thinking that we're not talking about current here anymore. We're talking about amperage, and I gotta train myself to talk that way. So he's correct in his comment to me. So yeah, how much amperage is being consumed in this circuit and how much energy. So, but yeah, I'll clean these up. I've already cleaned a lot of them up, but I took all that ice cube stuff out. This one, and I put in the one that you're using, but these drawings don't have those changes. So I'll make a key for you guys so you know exactly where those wires go connecting up to. And I'll make one without the keys, and the kids have to write in over here. Maybe I'll just put a line.
Yeah.
You fill in what that should be.
Yeah, that
Yeah.
sounds
Well,
great.
what I would do is using the one we give for them to do a lab, and then for their exam, they have to actually just complete the other one you have,
Yeah, there you go.
Yeah, that'd be great.
Yeah, because if you look at the very first one, it's very elementary. I mean, they're just looking at the data sheet, and if they have the data sheet in front of them,
Hmm.
they'll fill out that table. And then once they have the table,
Yeah.
they should reference it all the way through lab 3. And actually it's lab 4, because the first one is, okay, you tell me what you're doing. What is your theory of operation here? How are you going to keep this thing latched up? And now go do it.
Great.
Yeah, I love it. I love, but you're right, Andreas. I mean, if a student can do that, they can advance on.
Mm-hmm.
They get it.
Mhm. Yeah.
But also remember, I can't say this enough. The two things about a relay is one, it's a controlled isolation device. It controls high voltages, different voltages, mixed voltages. I can control it with a microcontroller, 5-volt. If I have like this thing here, I can go down, I think, as far as 3 volts on this guy. Control things, but I can also, if I look at, I think it can deliver 5 amps on the output. So I can do some pretty amazing things with that, but usually I use these as an interface between something a little larger. So anyway, I think we're almost to our end of our time. If I have any other labs that I can share with you guys, but you guys also have the I shouldn't say labs, videos. I'll share those with Marilyn, or I have your email addresses, they go right to you. I think you have all the stuff for the force sensor and the read switches and the light, right? The lighting, you have all that. I think you have those labs.
Yeah, we do.
Yeah, we do.
Yes. Mhm.
We do.
Okay. All right. Well, I'll clean things up to make it fall closer into what that relay that you're using, and then it'll make more sense. And then you could, I encourage you to hook it up. I mean, it is fun. And when you just put those 2 wires on, it changes everything. It's like, oh my gosh. And then when you think about how the power is flowing through the circuit, it just makes sense. And when you release the switch, it's already overcome that relay to turn it on, to give it another path around to keep the coil energized. So yeah, it's pretty cool. And then
Okay.
if we do PLC stuff, it even makes it funner, because then we can say, okay, hold that thought, but now let's do it in the PLC. So with like 1 line of code. So
I'll have to say everything that you're sharing with us is appreciated, because it's a nice bridge from where we are at a very introductory level to doing hands-on things with them.
yeah, and I just want to make another comment, and Andreas probably understands this because he's in that microcontroller world, and maybe even you, Judith, with the students you're working with. I probably will never go away from a breadboard. And part of that is I cut my teeth. I'm a little older probably than most. I've cut my teeth in the old days where, things had pins. We put them into breadboards. We tested them. I mean, I had transistor theory. I did all that stuff. And I had to since then kind of back off and not teach bipolar transistors and all this other stuff, because people are saying, my fellow instructors are going, what are you doing? That's all encompassed in something else. They don't need to know this. And I said, it's really nice to go into the break room, pour yourself a cup of coffee if you're a technician and turn to the engineer and say, I know why that solid state relay fried. It's
Mhm.
because we did this and the SCR couldn't handle this and this and this. It should have been a triac. And that engineer's going to go, you know what? You might be an engineering tech. We might want to move you in here and send you to school. But if you go, that thingy started smoking and I don't know what happened to it. It just melted. It's like, no, what's going on inside. And that's why the anatomy of a relay, it's just not this, it's this clicky thing that makes a noise. No, that's the spring pulling the contacts into position because the coil's overcoming it. So I'm this old school guy and I'll never get over it, Marilyn. So I apologize. My classes, I'll always have a little breadboard and I'll always have a couple resistors to say, this is what's happening. And you can take that now to a larger, bigger power structure, but this is what's happening in a small little breadboard. So anyway.
No, but I think people should have this foundational knowledge. I firmly believe that. I mean, I may not remember how to do a square root of a number, but I learned that in school and I know how it came. Even though I use my calculator, I cannot remember how it came. Even if you never use a transistor, but you're using the SSR and you know what you're controlling electrons and the foundational knowledge has to be there, I think.
Well, you probably had a professor that would write this elaborate lecture and then right in the middle he'd say, or she would say, and this is where the magic happens. And then you move on because it's like, well, tell us the theory. Tell us the theory. I want to know, just tell me the magic happens there, it just. So anyway, but
thank you so much. This is great.
Yeah, with my new center trainer, I really get into some very basic things with breadboard and, and calipers, and I love it. And I know if you took it out to industry, they might say, we don't use calipers and breadboards in industry. But I tell you what, the students who use my little trainer, the new one, they go, oh, I see how that coincides with the data sheet. I see what that means now. So.
Yeah, we have these beautiful trainers that Amatrol makes, right? For motors and control, and we're gonna use them, Judy, actually tomorrow. And but they don't see this, they don't see the components, right? I mean, they just see the where they plug the banana plugs and but your panel. So I have the panel that we made with you right next to it. So this is how real life looks like, and this is what you guys are doing just to learn it. I mean, I love Amatrol because it makes my life easier with the curriculum, right? But showing yours is together with that is fantastic. I think
it's more, I guess it's more raw. It's more raw. And I agree with you. There's wonderful trainers out there. Mine are more simplified or other people that do this, not me, other people do this, but I'm excited to release and I'm hoping to keep partnering with Marilyn because I want a vehicle to be able to launch some of the stuff my ideas, but I've got one on the floor over here that that's going to take the place of that one back there, which does the job just fine. But the new one kind of it's intriguing and it's fun and it's engaging. And that I think even for industry people, it should be fun. I mean, you can see what's going on the production floor and say, oh, I can kind of emulate that here. I can make something turn and I can see the speed of it with a sensor or whatever. But well, I will do a few things here, clean some things up. I'll share videos that I didn't share the first time, like Lingo if I didn't share it, and the relay one that shows you how to, own things out. Because I'm actually going through and telling you, what you should see, and I'll share those videos with Marilyn, or I'll get your addresses and I can put you in the Dropbox. So,
thank you.
Okay.
I'm curious. Are you at home or are you in your college?
I'm in Colorado.
But your building is your home. Are you he's at home?
Yeah.
Yes.
Yeah, home.
This is your house? Cool.
Yeah.
That's his playroom.
Nice. How come my wife sends me to the college? She doesn't let me do anything at home.
Yeah. It's, well, Marilyn was just here and I've got phase one of the little project done right next to me here, Marilyn. So
Yeah.
anyway,
All right. Well, I think we'll wrap this up. Thanks you guys for coming. Hopefully it was useful, and we'll get those files to you sometime in the next few weeks, I guess, couple weeks. What do you think?